going to ignore that you said that. Okay, chemistry 2 time. I want you to have a frame here without my shadow on it. If you choose to make this your cell phone background, as some people have, you just screenshot it, and then we'll move on. Lame, yeah. That did say lame. Each level lame. Okay, today we are talking about solutions chemistry. And we're going to do it fast because we never know what technological problems might present themselves partway through, making it so the video isn't. To that end, I'm going to talk to you first about the definition of a solution. And by that I mean you're going to talk to me while I drink my tea about the definition of a solution. Tell me.
1 second. You want to take that definition?
No, I want your definition. What are the components of a solution? I'll give you a sentence frame. Solutions are made from, this is layman's terms, I don't think a scientist would define it that way, something, solutes dissolved in solvents. I use this word specifically because that's the verb we use, which means for something to become a part of another thing. It has become in solution with. The method by which this happens is, I think, interesting, and we've talked about it before, but I'll tell you again. If we have, especially, let's think about an ionic compound. So if we have classically sodium chloride, the chlorine has what kind of charge? You're right, it's one of those. Which one? Okay, yeah, you got all three now. Which one is it for real, though? It's negative. And the sodium has what charge? Positive. If we pour sodium chloride into water, which does happen, give me a time when you might pour sodium chloride into water. I've been really on the James Bond thing lately. Give me a time when James Bond pours sodium chloride into water.
Trying to drug someone.
The opposite of that, trying to undrug himself.
Okay.
Remember the time that they try to poison him? They put the digitalis in his martini and he drinks it, and then he knows that he's been poisoned, so he takes a salt shaker and a little cup of water, and he drinks the whole salt, and like that, like we saw. You can't say his first name. You shouldn't accuse people on camera of doing tobacco. But when you dissolve salt in water, what's actually physically happening is that the little water molecule, which has a positive end and a negative end, interacts. You might understand that on the small scale, this one's a little deformed, don't worry about it. On the small scale, this sodium chloride is surrounded by these water molecules. That's what happens. The first thing when you pour the salt in, the water is surrounding it, and the negatively charged chlorine is attracted to the positive charged end, and I should have drawn this the other way. The positively charged sodium is attracted to the negative end of the water, and it is physically torn apart. You could say electromagnetically, but it is taken apart in the same way that, like this. See, look. It's like my hands are water molecules, and the lid is chlorine, and the marker is sodium. It's removed because of the electromagnetic force. And so that's what happens in dissolution. There are variations of that, and of course that can happen faster or slower, which we'll talk about. Let's just talk about it now. What are the 3 ways we could speed this process up? The 3 main, most basic ways that we could speed this process up of dissolution. Okay? Hold on, just give me one at a time. Increase surface area. And how would we do that in this case of salt?
So what should we put down? How to...
Oh yeah, sorry. Increase rate of dissolution. What's the word rate mean?
How fast?
Yep, how fast. So increasing the rate of dissolution. To speed up dissolution, we could increase the surface area. How do we do that in our example? If James Bond needed that salt to dissolve faster, how could he do it?
The water warm.
Well, we're not there yet. But in context of this one, if he had a choice, as he's walking by the tables in Royale Les Eaux, he can either pick between the salt shaker with little baby salt crystals or big coarse salt. Which one would he pick? Fine salt or coarse salt?
Coarse. Wrong. Fine.
Fine, because fine would have a higher surface area. So more ground up. The more ground up it is, the faster it'll dissolve. The more surface area it has, the faster it'll dissolve. Think about it this way. A single brick of salt, like a chunk of salt the size of your hand, would not dissolve instantly when it went in water, right? But if you had that same amount of salt as salt crystal, that individual like salt crystals you might buy at the store, that has a higher surface area. Basically, more of it is touching the water at any given time, and so it can dissolve faster.
So
what's another way?
Fine.
The finer it is, the finer you could say for salt grind, the faster it dissolves. Yeah, the finer the grain size, we would say in geology. Okay, what else could we do to increase the? Okay, increase. He did already say it.
Camera.
So in that scene of Casino Royale, not a sponsor, other movies are available, but he goes into the bathroom and he fills his cup full of water. Would he, if he knew the chemistry, pick cold water or hot water? Hot, because it dissolves faster. Okay, yeah, that's actually not wrong, but it's more because, or we usually think of it as because the molecules are moving faster. The water molecules are moving faster. They're more likely to bump into the sodium or chlorine because they're moving faster, and they're therefore more likely to rip it apart. In the same way, the tea that we drink, we usually, not always, but usually dissolve in hot water because the compounds that are in the tea that can be dissolved, like hair. No, that's a reference you won't understand because we had to start the video over. But the compounds in tea that can be dissolved are are more quickly dissolved in hot water. So it's faster to make tea using hot water and then cool it down afterward as opposed to letting it sit in cold water. And what's the final one? What's the final rate of dissolution increase method?
I know it.
Agitation.
Define, other than, apart from the context in which me trying to teach Chem 2 is agitation for me, define agitation in this context. I'm sorry.
The more aggressive the bear is eating you, the faster it gets eaten. So, the more molecules.
It is fun that, it's also fun that the mic can almost certainly pick up what you're saying way better than what I'm saying because you're just yelling. Like I was just telling the 8th graders, the 8th graders a couple weeks ago about how when you talk, it's not actually the air from your mouth coming into my ears, but in your case it is. Like I can feel, I'm about to be knocked over by how loud you're talking. Go on.
So the more molecules, or in this place, hydrogen and oxygen.
Yeah.
If it's warm, especially, they're aggressively trying.
What are they doing more of? In the same kind of like when we increase the temperature. They're
more aggressive.
They're more.
They're agitating, so they're messing with it more.
They're moving around more. Is what we're getting at.
If you were to put butter in a room temperature setting, it's gonna melt eventually. But if you put it in an oven, it's gonna melt instantly.
Again, that's a temperature one though.
But we're using it in the agitation one.
Well, you can't just say that. You can
So
just.
you slap butter.
Okay.
Compared to when you beat butter, the butter will expand more when you beat it than when you slap it.
I acknowledge that you have spoken. The way that I would probably choose if I was going to say it, I would say that stirring will make things dissolve faster. Usually we would use the word stirring. Shaking, sure. Oh, again, there's a James Bond joke in there too. Shaken, not stirred, etc. James Bond, as he tries to drink that salt water so that he can then induce vomiting, would shake it, or I mean, he can't help it because his whole body shaking has been poisoned. But if he had more time, he could stir it, and that would make sure more salt gets dissolved. Stirring, warming, making finer. I mean, if you had to use one single word, you could probably say grinding. We usually grind things up to make them increase in surface area. So that's how solutes, which are the things being dissolved, dissolve in solvents, which are the things that do the dissolving. Now, how do we measure this? Well, the qualitative way, very simply, if we were to compare, how would we qualitatively, if I was going to ask you what is the concentration of this tea, how could you answer qualitatively?
Say that one more time.
What's the concentration of the tea? Yeah, no, that's a temperature. What's the concentration of this tea?
Let me make it louder for the camera.
I'm trying not to give it away. You could say, compared to if the tea were to sit longer, this tea would be
Stronger.
Yeah, it would get stronger as we sit longer. So we usually use those terms strong or weak in terms of solution for qualitative. So you could write that down. So qualitatively, we say a solution is either strong or weak, and that's obviously that's relative. How strong it is or how weak it is relative. But we do, and that is a useful thing. Please don't do that. Let's take notes on our own notebooks. If we had lemonade and we made the lemonade powder in a quart of water versus making that same amount of lemonade powder in a half gallon of water, the half gallon one would be weaker, right? That we would end up with less solute per solvent. But we do, when we measure them quantitatively, there are really, chemically, we use two main ways. And I'm not going to tell you the percent by volume or percent by mass ones because in my opinion those calculations are easy. You should just know them, and they're also something that you use outside of this class. But the ones that we learned for chemistry are molarity and molality.
I hate molality.
Okay, you're not the only one with that opinion, but you shouldn't have it. Molarity is you use the abbreviation capital M, and we also use that as the unit, moles per liter, equals N, which is amount, over volume. So where capital M is molarity, measured in moles per liter, N is amount in moles, and capital V is volume measured in liters. And this does have to be, the volume is of the whole solution, and the amount is of the solute. In molality, on the other hand, which is lowercase m, they just couldn't make it more confusing. It's amount, but it's now divided by mass. So that's confusing. We've got two lowercase m's. I've never actually noticed that before. I'm not happy with that. But this m, molality, measured in moles per kilogram, is defined as the amount in moles of the solute divided, this is where it gets a little bit tricky, this m, mass, in kilograms, but not of the solution, but kilograms of the solvent. So in this one, in molarity, it's divided by how much total stuff there is at the end, and in molality, it's divided by the mass of just what was doing the dissolving. And that, I would say, is the fundamental or the primary difference. I mean, obviously, molality is about mass, where molarity is about volume. But the fundamental difference is whether we're dividing by solvent or solution, amount of solvent or solution. And what do we do with this? What do we do with concentration? Solve. That's right. Dissolve. Actually, those words are related. Solution and dissolution. Solve and solvent. Dissolve, yeah. That's what I should have said. What we do with those is the most important, probably practical concern for the calculation of this are what are called colligative properties. Colligative properties. Colligative properties means those properties that have to do with the amount of it. The word colligative means regarding how much, regarding the quantity. And by that it means that they vary based on how much stuff there is, but not the kind of the stuff. Like it's not different properties, whether it's sodium chloride or calcium chloride or potassium chloride, but it is different by how much stuff there is, period. And the colligative properties are boiling point elevation, and freezing point depression. I think if you had a band from like around the Great Lakes or Alaska, or certainly from Siberia, and you called it freezing point depression, and you were an emo band, I think that would be really good. Boiling point elevation, freezing point depression. These are colligative properties. They have to do with how saturated the solution is. And that's, by the way, that's another way that we talk about the concentration of a solution is how saturated it is. Basically, each solution, I'm going to draw a little scale up here. Each solution has a certain amount of solute that it can dissolve, and it's considered saturated. Did you hear what I said? I said each solution has a certain amount of solute. I'm going to define that. Certain amount of solute which can be dissolved. At a given what, do you think? Yes, exactly right. At a given temperature. So if you read about the solubility of different stuff, which you will as you come across them in your chapter review, and actually this becomes more important in the next couple chapters, but as you read about the solubility of different chemical species, it'll give it to you in usually in grams per liter of water or hexane or whatever the solvent is, grams per liter at a certain temperature. So it'll say the sodium chloride can dissolve, I don't know what it is, but it'll be a certain amount of mass per liter of water at 4 degrees Celsius, for instance. If it has less than how much it could possibly have at that temperature, we would call that what? Well, if saturated was as much as it can hold, less than that amount would be unsaturated.
Certain amount of solid.
Certain amount of solute which can be dissolved at a given temperature. And if it, and sometimes under certain conditions we can have more than we can technically be dissolved at that certain temperature. And we would call that somebody else's.
Super saturated.
Yeah, I gave you the entire thing. And I also spelled it wrong. Super saturated. So what happens when something is super saturated is you can dissolve as much as it can hold at a certain temperature and then lower the temperature and it'll stay dissolved, but now it's technically super saturated. And that's an interesting state because then if you put in a seed crystal, the whole thing crystallizes, and that's what we'll do in the lab if there's time, which I expect there to be. So how saturated the solution is tells us about the colligative properties. The more saturated it is, the higher the boiling point gets, boiling point elevation, and the lower the freezing point gets, freezing point depression. The more saturated, the higher the boiling point. And the more saturated, the lower the freezing point. Can you think of a time, or sometimes, when this might be useful? When might it be useful to elevate the boiling point?
When you're cooking eggs.
Yeah, exactly right. Amazing response. Yeah, if you're boiling something, how hot something is pretty much equal to how fast it cooks. Obviously, there are other things to consider. But if you are boiling something, normally water will only boil at a certain temperature for whatever pressure you live in. And if you add solvent or solute to it, if you add salt, for instance, because that's non-toxic, but if you add any solute to it, it'll make the boiling point higher, which means the cooking temperature will be higher, which means your eggs can cook faster, or noodles, or whatever.
Salt in water, it boils faster.
It probably, you mean like it starts to boil faster?
Yeah.
Well, it probably is already, I would guess that when you are adding the salt itself and you notice more bubbles, it's because you're providing more nucleation points for the bubbles to form. I think it's probably not actually boiling faster, because then I would guess pretty quick after that it calms right down, and then 5 or some minutes later, now it'll start to boil up again.
This is just a lie.
What is just a lie? The thing I said?
Salt
You're calling me a liar right now?
No,
To my
salt.
face on video?
No! But salt in water makes it boil faster, which is just wrong. Just makes it bubble faster, but really it's just not even.
Yeah, maybe you could make a case for that it can absorb more energy because the boiling point is higher too. I don't think it makes it boil faster. What it really does is it raises the boiling point so that now it can cook hotter.
But it would make it take longer.
Well,
to
how?
boil.
I'll tell you how. This is the equation for it. We'll do the math of it. Delta TB equals K. Don't forget this Van 't Hoff factor. KBMI. Again, your book, I think this book is out of print, so I'll just say it. At Glencoe Chemistry, Matter and Change, copyright 2008, is wrong. It doesn't include what's called the Van 't Hoff factor here.
Yeah, and that's when you add that number.
Yeah, you multiply it by that number, but you're right. You include that number is what you meant. That I is the Van 't Hoff factor. And so what we have here is the change in boiling point. Capital T is temperature. The change in the boiling point in degrees Celsius is equal to the molal boiling point elevation constant, which is true for any given substance. So you look up Kb on a table, or you're usually given Kb, multiply it by the molality, which was over here, and then multiply it by the Van't Hoff factor, which this also applies to freezing point depression. And the Van't Hoff factor is how many, it's an integer, how many species liberated, I'm going to talk about this in a second, when dissolved.
How many species
Liberated when dissolved. What does liberate means? You might remember from social studies of some kind.
Liberate is when you become a Democrat.
That's liberalate. That's not a real word. Liberalate. No. You know the word liberate.
How many they grow?
Set free was what liberate means. So in our example up here, 2 species are liberated. It was sodium chloride. Now it's sodium ion and chloride ion. And so there are 2. You remember talking about this a little while ago?
Yeah.
So 2 species, sodium ion, chloride ion. If it were calcium chloride, hey, stop whispering behind my back and listen. If it were calcium chloride, CaCl2, what would the Van't Hoff factor be?
2.
No, 3, because there's 1 calcium and 2 chlorines. So 3. When it's torn apart, there are now 3 things. What if it were, we did this one in class the other day, what if it were ammonium chloride? 5, yeah. 1 ammonium ion, 4 chloride ions is 5. So that has a Van't Hoff factor of 5. That one has a Van't Hoff factor of 3. Sodium chloride has a Van't Hoff factor of 2. And remember, any covalent is just 1. The Van't Hoff factor of covalent compounds is just 1. So sugar and alcohol are common covalent solutes. So we just...
Stay away from both of them.
That's right.
Correct.
Excellent recommendation for the video.
Kids.
No, they can't hear you, but I'll tell them for you.
Kids.
Kids, Taylor says.
Don't
do drugs.
I mean alcohol.
Or
eat Little Debbie Donuts.
Or eat Little Debbie Donuts,
Or
which are
don't be
sugar.
an alcoholic fatty.
I'm not going to say that part, but they probably will have heard it. So
Red Ribbon Week.
That's right. This is at Red Ribbon Week. I should include that. I should put my first, what do you call those little ats? What are those? Hashtag. That's not an at. I'll put a hashtag on here for the first time ever. So this is my Red Ribbon Week, which is a really hard thing to say, video. The one for freezing point depression is delta TF equals K sub F times the molality times the Van't Hoff factor. And then in both of these cases, since it's change in whatever it is, we would add in the boiling point or subtract in the freezing point from the original ones. So the values you need to solve these are original